Thanks so much for having me. I am here today on behalf of Isaac Buo, who is the creator of all of this work. He is a PhD student in Estonia and spent a year in my lab at ASU to work on this project. And unfortunately, they wouldn't let him Zoom into his PhD defense, which happens in 6 hours from now. So I'm giving this presentation, and then 6 hours from now, a similar presentation will be held in Estonia as part of his PhD defense. So I'll be talking about high-resolution thermal exposure and shade maps for cool corridor planning in Phoenix. And let me see if I can click the right button. Okay, I found it. So why are we interested in shade and mean radiant temperature in Phoenix? Well, it is actually quite hot in Phoenix. Just as I left a couple of days ago, we got another heat wave. It was 47 degrees Celsius today, which is 10 degrees above normal for this time of year. You can bake cookies in the car. People have attempted to bake pizza in a car, and we had a record-breaking streak of 31 days of over 42 degrees Celsius maximum temperatures in July, which I missed because I was traveling, but it was fairly hot. So now the city of Phoenix is at the forefront of heat research. They're the first city in the nation to have a publicly funded, a taxpayer-funded heat mitigation office. And they are doing various things to try to keep people cool in the summer. And they just recently started a cool corridor program, which aims to create 100 cool corridors across the whole city proper, so that wherever you live in the city, within about 20 minutes of a commute or bike ride, you could get to a cool corridor if needed. There was funding in 2022 made available to plant 1,800 trees, which doesn't sound like a lot, but it's really important to place these trees where people are as opposed to spreading them all across the city. And the city is currently figuring out a ranking system on how to decide where to place these cool corridors and where to plant these trees. And they look at heat vulnerability in neighborhoods. They look at how dependent people are on public transit, if they need to use the bus. There are not a lot of bus lines in Phoenix. They look at how they look at pedestrian traffic, and they also look at the overall shade coverage and the temperature in the city. And this is where this project comes in. Shade in Phoenix is really important. There was a recent commentary that one of my colleagues, Kelly Turner from UCLA, and a colleague from ASU, Jennifer Van Ost, and I wrote that highlights the importance of shade in hot and dry, sunny environments because the shortwave radiation that hits you when you're not standing in the shade is the main contributor to the heat load on your body when you're in the outdoor environment in the summer in such an environment. You also have the long wave radiation from hot surfaces that hits you from the ground and then reflected shortwave and diffuse, but the direct incoming shortwave is the main driver of your heat load and also the main driver of your thermal stress when you're in these situations. So the goal of Isaac's study was to produce high resolution mean radiant temperature or heat load maps and also shade maps for a hot summer day to see where are the shade deserts in Phoenix downtown and in the whole city proper, so that the city can use this information to make better decisions on where to target their heat mitigation strategies. We used the Solveig model and used LiDAR data to generate the input files. And then we ran the model and we generated shade maps to see if sidewalks in Phoenix actually meet a minimum requirement of 20% shade. There was a recent Maricopa Association of Government report that came out. It's an active transportation plan. And they said desirably, if you have a sidewalk that leads up to a bus stop, it should have about 20% shade so that you can safely walk to that bus stop. So we ran the Solveig model. We evaluated it using in situ measurements, and we'll see how that went. So this is the methodology. Does this have a pointer? It does. So we used the LiDAR data to create surface models, a building layer, a tree layer, and a surface layer. And then together with weather data from a nearby weather station, we fed this into the Solveig model. The Solveig model gives us 1 meter resolution mean radiant temperature maps. But mean radiant temperature, again, is the heat load on the human body. And then Solveig also can create shade maps, and it's at an hourly basis. So we ran the model for a hot, sunny day in the summer of, I think it was 2012. Then once we retrieved these two maps of interest, we first did a validation using in situ measurements. And then in the next step, we intersected the shade map with sidewalk polygons in the city to calculate the sidewalk shade coverage on these sidewalks. And we generated these sidewalk polygons using a buffer analysis because the city of Phoenix, unfortunately, does not have a sidewalk layer in their GIS. So there we go, model validation. We used the MARDI card, which is a human biometrological garden card that has net radiometers attached to it that measure the shortwave and longwave radiation in all 6 directions, and that can then yield the mean radiant temperature at a given location. MARDI also has an air temperature and humidity sensor that's in this radiation shield right here. MARDI has a GPS so that we don't lose him when we're on the road. And then MARDI has a wind sensor that measures the horizontal wind speed and the horizontal wind direction. These are places in Arizona, in the city of Tempe, which is very close to the city of Phoenix. This is the, where's my pointer? Well, to the left, you can see the ASU Tempe campus. We found various locations on campus that represent a very diverse urban form, from shade under trees to shade from the urban form, open spaces, spaces on parking lots, and to cover a variety of situations that couldn't occur in the urban environment. And then on top of that, there we go. On top of that, we measured at a park in Tempe. It's a very popular public park. A lot of people spend time there on weekends to take their kids to playgrounds. And we measured specifically tree shade in this park, and also various locations that were overgrass that we couldn't find on the ASU campus. So after we've done all these measurements, we did a validation. So we ran Solveig using airport data to force the model, and then we calculated the root mean square error, the R square, and a bunch of other statistical metrics to see how well the model performed. And here are those numbers. If you look at the root mean square error, overall, it was slightly above 5. It was 5.6 degrees Celsius, which is 0.6 degrees Celsius over the recommended threshold of 5 degrees from the ISO standard. It was performing a little bit better overall for shade. It was 5.1 degrees Celsius, not as good for sun-exposed locations, and then was actually doing really well for building canyons. And then there's the arrow bars and the charts to the right to give you an overview of this visually. So now these are the resulting mean radiant temperature maps from Solveig. Overall, and this is Phoenix, MRT for this day peaked at 83 degrees Celsius, and MARDI measured about 80 degrees Celsius. So it's fairly close to what you actually would experience if you walk over a parking lot in Phoenix at a 110 degree or 42 degree day in the summer. In the shade, mean radiant temperature was very close to air temperature, which was to be expected. So it was about 41 degrees Celsius during the hottest time of day. If you look at the downtown areas, both downtown Phoenix and downtown Tempe, there's a downtown Tempe snapshot that's blown up to the right. And then downtown Phoenix is the shade of blue that you see right in the center. It's very tiny. So these areas have higher buildings, and the streets are not as wide. So these areas experience lower mean radiant temperatures because of the shade from the urban form. We ran the model hourly from 8 o'clock in the morning to 8 o'clock at night. So as you approach the nighttime and just after sunset, mean radiant temperature was very close again to air temperature, which is, I mean, there is some variation, but it's there are not that dramatic differences that we would see during the daytime in terms of mean radiant temperature. So now the shade distribution, that's this chart here. Again, similar pattern. So you see more shade coverage in the downtown area, which is the tiny black dot in the center, and then the Tempe downtown area is blown up over here. So these areas had more shade because of the urban form, and also a little bit more tree canopy cover in Tempe. And then the dark patches that you see down there, this were missing data. So that doesn't mean that there is a huge mountain there. It was just missing data. So now with this shade map, what Isaac did is he created sidewalk buffers for the whole city of Phoenix and Tempe to be able to calculate how much shade coverage is there actually on these sidewalks as you would walk to the bus stop, for example. So there are some examples here, some example snapshots from the shade cover. The north-south sidewalks generally were more shaded than the sidewalks in any other direction. Most of our street network in Phoenix is north, south, east, west. So it's quite boring. During midday, the shade coverage, as to be expected, was very low for the sidewalks. There was hardly any sidewalk that had 20% coverage in the city, and only 8% of the sidewalks in the study area actually met the 20% shade goal that's outlined in the Maricopa Association of Government Action Plan. And most sidewalks reach the shade coverage at 7 o'clock, but that's not surprising because sunset is at 7:30. So all the tall buildings and even the tiniest, even trash bins would probably cast a shadow on you by then. To summarize, I think I have 1 minute left. The Solveig estimates were actually quite reasonable. They were very close to the recommended threshold of 5 degrees Celsius. I do have to say that we did not use a land cover data set as a basis to actually model the fluxes from the ground surface. So currently everything's assumed to be paved, and that's an improvement Isaac is currently working on. Some of the larger errors we saw was because there was a mismatch between how Marty was placed in a certain shade type and how Solveig actually modeled the shade based on the 3D geometry. But overall, we were quite happy with the result. Most of the area in Tempe and Phoenix is not walkable. That's not a surprise. Most of the sidewalks did not meet the 20% shade goal. And the downtown areas, Phoenix and Tempe, had quite a decent shade cover throughout the day because of the taller buildings. So these maps that Isaac created are actually now being used by the city to make decisions on their cool corridor locations. So that's good to see, and hopefully we can improve a little bit on the MRT results moving forward. So if you're interested in this paper, there is a QR code. You can download it. It just got published earlier this year. Here's actually, it's working an animation of the shade progression in Tempe downtown throughout the day. And with that, I'm happy to take questions.
Thank you, Ariane. Any questions in the room for Ariane? There's a question up here, and then one over the other side.
Really great. I was wondering, for the Solveig model, you provide some input for air temperature and humidity, right?
Mm-hmm.
Do you provide a single value or have some gridded estimate?
Yes, at this point we only use a single value. I know we could do better on that, but we only use we found a weather station. So we use Sky Harbor. Sky Harbor is biased towards paved surfaces, and we also use the station that's part of the AZMet network. I'm going to talk about this on Thursday if you're interested. It's a different talk. But that network is it's in the urban area, so it's more representative of the actual environment in Phoenix and Tempe. But yeah, I mean, ideally you would like to grid the model and force it with more localized air temperature, humidity, and wind speed at the different places around the city. Yes.
There was one question in the back. Mike is coming. We only have one left. Yeah.
Thank you. How do you move Marty around without some bias from whoever's pushing Marty around?
Oh yeah, so I didn't talk about the actual procedure. We actually leave Marty alone. So we yeah, we don't want to mess with his sensors. So what we do is we identify points of interest and we move him to these points, and then we hide behind a tree. So that Marty doesn't see us, but Marty only sees the environment. And we do this for about a minute or two because the sensors require 45 seconds or so to adjust to the new situation because they have a slight sensor lag. And then during this time, we hide, and then we pick him back up and take him to the next spot.
Thank you.
Thank you very much, Ariane. Let's thank Ariane again. Next up, we've got Dr. Jan